in its global ocean, covering 70. Mars is the fourth planet and the furthest terrestrial planet from the Sun. The reddish color of its surface is due to finely grained iron, 3, oxide dust in the soil, giving it the nickname the Red Planet. Mars's radius is second smallest among the planets in the Solar System at 3,389.5 kilometers, 2,106 miles. The Martian dichotomy is visible on the surface. On average, the terrain on Mars's northern hemisphere is flatter and lower than its southern hemisphere. Mars has a thin atmosphere made primarily of carbon dioxide and two irregularly shaped natural satellites, Phobos and Deimos. Geologically, Mars is fairly active, with dust devils sweeping across the landscape and Mars quakes, Martian analog to earthquakes, trembling underneath the ground. The surface of Mars hosts a large shield volcano, Olympus Mons, and one of the largest canyons in the Solar System, Valles Marineris. Mars's significant orbital eccentricity and axial tilt cause large seasonal changes to the polar ice cap's coverage, and temperature swings between 110 degrees C, 166 degrees F, to 35 degrees Celsius, 95 degrees Fahrenheit, on the surface. A Martian solar day, Sol, is equal to 24.5 hours and a Martian solar year is equal to 1.88 Earth years. Like the other planets in the Solar System, Mars was formed approximately 4.5 billion years ago. During the Noachian period from about 4.1 to 3.7 billion years ago, Mars's surface was marked by meteor impacts, valley formation, erosion, and the possible presence of water oceans. The Hesperian period from 3.7 to 3.22 billion years ago was dominated by widespread volcanic activity and flooding that carved immense outflow channels. The Amazonian period, which continues to the present, was marked by the wind's influence on geological processes. It is unknown whether life has ever existed on Mars. Mars is among the brightest objects in Earth's sky, and thus has been known from ancient times. Its high contrast albedo features make it a common subject for viewing with a telescope. Since the late 20th century, Mars has been explored by uncrewed spacecraft and rovers, with the first flyby by the Mariner 4 probe in 1965, the first Mars orbiter by the Mars 2 probe in 1971, and the first landing by Viking 1 in 1976. As of 2023, there are at least 11 active probes orbiting Mars or at the Martian surface. Currently, Mars is an attractive target for the first future interplanetary human missions. Mars is approximately half the diameter of Earth, with the surface area only slightly less than the total area of Earth's dry land. Mars is less dense than Earth, having about 15% of Earth's volume and 11% of Earth's mass, resulting in about 38% of Earth's surface gravity. The red-orange appearance of the Martian surface is caused by ferric oxide, or rust. It can look like butterscotch. Other common surface colors include golden, brown, tan, and greenish, depending on the minerals present. Like Earth, Mars has differentiated into a dense metallic core overlaid by less dense materials. Current models of its interior imply a core consisting primarily of iron and nickel with about 16–17% sulfur. This iron, 2-sulfide core is thought to be twice as rich in lighter elements as Earth's. The core is surrounded by a silicate mantle that formed many of the tectonic and volcanic features on the planet, but it appears to be dormant. Besides silicon and oxygen, the most abundant elements in the Martian crust are iron, magnesium, aluminium, calcium, and potassium. The average thickness of the planet's crust is about 50 kilometers, 31 miles, with a maximum thickness of 125 kilometers, 78 miles. By comparison, Earth's crust averages 40 kilometers, 25 miles, in thickness. Mars is seismically active. In 2019, it was reported that InSight, now offline, had detected and recorded over 450 Mars quakes and related events. In 2021 it was reported that based on 11 low-frequency Mars quakes detected by the InSight lander, the core of Mars was indeed liquid and had a radius of about 1830 plus or minus 40 km and a temperature around 1900–2000 K. The Martian core radius is abnormally large, accounting for more than half the radius of Mars and about half the size of Earth's core. To this, it has been suggested that the core contains some amount of lighter elements like oxygen and hydrogen in addition to the iron-nickel alloy and about 15% of sulfur. The core of Mars is overlaid by the rocky mantle, which does not seem to have a thermally insulating layer analogous to the Earth's lower mantle. The Martian mantle appears to be solid down to the depth of about 500 kilometers, where the low-velocity zone, partially melted asthenosphere, begins. Below the asthenosphere the velocity of seismic waves starts to grow again, and at the depth of about 1050 kilometers lies the boundary of the transition zone extending down to the core. Further analysis of InSight data has suggested that Mars has a liquid core. Mars is a terrestrial planet with a surface that consists of minerals containing silicon and oxygen, metals, and other elements that typically make up rock. The Martian surface is primarily composed of tholeiitic basalt, although parts are more silica-rich than typical basalt and may be similar to andesitic rocks on Earth, or silica glass. Regions of low albedo suggest concentrations of plagioclase feldspar, with northern low albedo regions displaying higher than normal concentrations of sheet silicates and high silicon glass. Parts of the southern highlands include detectable amounts of high calcium pyroxenes. Localized concentrations of hematite and olivine have been found. Much of the surface is deeply covered by finely grained iron, oxide dust. Although Mars has no evidence of a structured global magnetic field, observations show that parts of the planet's crust have been magnetized, suggesting that alternating polarity reversals of its dipole field have occurred in the past. This paleomagnetism of magnetically susceptible minerals is similar to the alternating bands found on Earth's ocean floors. One theory, published in 1999 and re-examined in October 2005, with the help of the Mars Global Surveyor, is that these bands suggest plate tectonic activity on Mars 4 billion years ago, before the planetary dynamo ceased to function and the planet's magnetic field faded. The Phoenix lander returned data showing Martian soil to be slightly alkaline and containing elements such as magnesium, sodium, potassium, and chlorine. These nutrients are found in soils on Earth. They are necessary for growth of plants. 56 experiments performed by the lander showed that the Martian soil has a basic pH of 7.7, and contains 0.6% of the salt perchlorate, concentrations that are toxic to humans. Streaks are common across Mars and new ones appear frequently on steep slopes of craters, troughs, and valleys. The streaks are dark at first and get lighter with age. The streaks can start in a tiny area, then spread out for hundreds of meters. They have been seen to follow the edges of boulders and other obstacles in their path. The commonly accepted theories include that they are dark underlying layers of soil revealed after avalanches of bright dust or dust devils. Several other explanations have been put forward, including those that involve water or even the growth of organisms. Radiation levels on the surface are on average 0.64 millisieverts of radiation per day, and significantly less than the radiation of 1.84 millisieverts per day or 22 millirads per day during the flight to and from Mars. For comparison, the radiation levels in low Earth orbit, where Earth's space stations orbit, are around 0.5 millisieverts of radiation per day. Hellas Planitia has the lowest surface radiation at about 0.342 millisieverts per day, featuring lava tubes southwest of Hadriacus Mons with potentially levels as low as 0.064 millisieverts per day. Mars is the fourth planet and the furthest terrestrial planet from the Sun. The reddish color of its surface is due to finely grained iron, oxide dust in the soil, giving it the nickname the Red Planet. Mars's radius is second smallest among the planets in the Solar System at 3,389.5 kilometers, 2,106 miles. The Martian dichotomy is visible on the surface. On average, the terrain on Mars's northern hemisphere is flatter and lower than its southern hemisphere. Mars has a thin atmosphere made primarily of carbon dioxide and two irregularly shaped natural satellites, Phobos and Deimos. Geologically, Jupiter is the fifth planet from the Sun and the largest in the Solar System. It is a gas giant with a mass more than 2.5 times that of all the other planets in the Solar System combined, and slightly less than 1/1000th the mass of the Sunday. Jupiter orbits the Sun at a distance of 5.200, 778.5 gm, with an orbital period of 11.86 years. Jupiter is the third brightest natural object in the Earth's night sky after the Moon and Venus, and it has been observed since prehistoric times. It was named after Jupiter, the chief deity of ancient Roman religion. Jupiter was the first planet to form, and its inward migration during the primordial solar system impacted much of the formation history of the other planets. Jupiter is primarily composed of hydrogen, 90% by volume, followed by helium, which makes up a quarter of its mass and a tenth of its volume. The ongoing contraction of Jupiter's interior generates more heat than the planet receives from the Sunday. Its internal structure is believed to comprise an outer mantle of liquid metallic hydrogen, and a diffuse inner core of denser material. Because of its rapid rotation rate of 1 rotation per 10 hours, Jupiter's shape is an oblate spheroid. It has a slight but noticeable bulge around the equator. The outer atmosphere is divided into a series of latitudinal bands, with turbulence and storms along their interacting boundaries. The most obvious result of this is the Great Red Spot, a giant storm which has been observed since 1831 and possibly earlier. Jupiter is surrounded by a faint planetary ring system and has a powerful magnetosphere, the second largest contiguous structure in the solar system, after the heliosphere. Jupiter forms a system of 95 known moons and probably many more, including the 4 large moons discovered by Galileo Galilei in 1610, Io, Europa, Ganymede, and Callisto. Ganymede, the largest of the 4, is larger than the planet Mercury. Callisto is the second largest. Io and Europa are approximately the size of Earth's moon. Since 1973, Jupiter has been visited by 9 robotic probes, 7 flybys and 2 dedicated orbiters, with 2 more either en route or awaiting launch. Jupiter is believed to be the oldest planet in the solar system. Current models of solar system formation suggest that Jupiter formed at or beyond the snow line, a distance from the early Sun where the temperature was sufficiently cold for volatiles such as water to condense into solids. The planet began as a solid core, which then accumulated its gaseous atmosphere. As a consequence, the planet must have formed before the solar nebula was fully dispersed. During its formation, Jupiter's mass gradually increased until it had 20 times the mass of the Earth, approximately half of which was made up of silicates, ices and other heavy element constituents. When the proto-Jupiter grew larger than 50 Earth masses, it created a gap in the solar nebula. Thereafter, the growing planet reached its final mass in 3-4 million years. According to the Grand Tack hypothesis, Jupiter began to form at a distance of roughly 3.50, 520 million km, 330 million mi, from the Sunday. As the young planet accreted mass, interaction with the gas disk orbiting the Sun and orbital resonances with Saturn caused it to migrate inward. This upset the orbits of several super-Earths orbiting closer to the Sun, causing them to collide destructively. Saturn would later have begun to migrate inwards too, much faster than Jupiter, until the 2 planets became captured in a 3:2 mean motion resonance at approximately 1.50, 220 million km, 140 million mi, from the Sunday. This changed the direction of migration, causing them to migrate away from the Sun and out of the inner system to their current locations. All of this happened over a period of 3-6 million years, with the final migration of Jupiter occurring over several 100,000 years. Jupiter's migration from the inner solar system eventually allowed the inner planets including Earth to form from the rubble. There are several unresolved issues with the Grand Tack hypothesis. The resulting formation timescales of terrestrial planets appear to be inconsistent with the measured elemental composition. It is likely that Jupiter would have settled into an orbit much closer to the Sun if it had migrated through the solar nebula. Some competing models of solar system formation predict the formation of Jupiter with orbital properties that are close to those of the present-day planet. Other models predict Jupiter forming at distances much farther out, such as 18O, 2.7 billion km, 1.7 billion mi. Based on Jupiter's composition, researchers have made the case for an initial formation outside the molecular nitrogen, N2, snowline, which is estimated at 2030 3.04.5 billion km, 1.92.8 billion mi, from the Sun, and possibly even outside the Argon snowline, which may be as far as 40 6.0 billion km, 3.7 billion mi. Having formed at one of these extreme distances, Jupiter would then have, over a roughly 700,000 year period, migrated inwards to its current location. During an epoch approximately 2-3 million years after the planet began to form. In this model, Saturn, Uranus, and Neptune would have formed even further out than Jupiter, and Saturn would also have migrated inwards. Jupiter is a gas giant, being primarily composed of gas and liquid rather than solid matter. It is the largest planet in the Solar System, with a diameter of 142,984 kilometers, 88,846 miles, at its equator, giving it a volume 1,321 times that of the Earth. Its average density, 1.326 g/cm3, is lower than those of the four terrestrial planets. By mass, Jupiter's atmosphere is approximately 76% hydrogen and 24% helium, though, because helium atoms are more massive than hydrogen molecules, Jupiter's upper atmosphere is about 90% hydrogen and 10% helium by volume. The atmosphere also contains trace amounts of methane, water vapor, ammonia, and silicon-based compounds, as well as fractional amounts of carbon, ethane, hydrogen sulfide, neon, oxygen, phosphine, and sulfur. The outermost layer of the atmosphere contains crystals of frozen ammonia. Through infrared and ultraviolet measurements, trace amounts of benzene and other hydrocarbons have also been found. The interior of Jupiter contains denser materials. By mass, it is roughly 71% hydrogen, 24% helium, and 5% other elements. The atmospheric proportions of hydrogen and helium are close to the theoretical composition of the primordial solar nebula. Neon in the upper atmosphere only consists of 20 parts per million by mass, which is about a tenth as abundant as in the Sun. Jupiter's helium abundance is about 80% that of the Sun due to precipitation of these elements as helium-rich droplets, a process that happens deep in the planet's interior. Based on spectroscopy, Saturn is thought to be similar in composition to Jupiter, but the other giant planets Uranus and Neptune have relatively less hydrogen and helium and relatively more of the next most common elements, including oxygen, carbon, nitrogen, and sulfur. Those planets are known as ice giants, because the majority of their volatile compounds are in solid form. Jupiter with its moon Europa on the left. Earth's diameter is 11 times smaller than Jupiter, and 4 times larger than Europa. Jupiter's mass is 318 times that of Earth, 2.5 times that of all the other planets in the Solar System combined. It is so massive that its barycenter with the Sun lies above the Sun's surface at 1.068 solar radii from the Sun's center. Jupiter's radius is about 1/10 the radius of the Sun, and its mass is 1/1000th the mass of the Sun, as the densities of the two bodies are similar. A Jupiter mass, mj or mjup, is often used as a unit to describe masses of other objects, particularly extrasolar planets and brown dwarfs. For example, the extrasolar planet HD 209,458b has a mass of 0.69 mj, while the brown dwarf Gliese 229b has a mass of 60.4 mj. Theoretical models indicate that if Jupiter had over 40% more mass, the interior would be so compressed that its volume would decrease despite the increasing amount of matter. For smaller changes in its mass, the radius would not change appreciably. As a result, Jupiter is thought to have about as large a diameter as a planet of its composition and evolutionary history can achieve. The process of further shrinkage with increasing mass would continue until appreciable stellar ignition was achieved. Although Jupiter would need to be about 75 times more massive to fuse hydrogen and become a star, its diameter is sufficient, as the smallest red dwarf may be only slightly larger in radius than Saturn. Jupiter radiates more heat than it receives through solar radiation, due to the Kelvin-Helmholtz mechanism within its contracting interior. This process causes Jupiter to shrink by about 1 mm, 0.039 in/year. At the time of its formation, Jupiter was hotter and was about twice its current diameter. Before the early 21st century, most scientists proposed one of two scenarios for the formation of Jupiter. If the planet accreted first as a solid body, it would consist of a dense core, a surrounding layer of liquid metallic hydrogen, with some helium, extending outward to about 80% of the radius of the planet, and an outer atmosphere consisting primarily of molecular hydrogen. Alternatively, if the planet collapsed directly from the gaseous protoplanetary disk, it was expected to completely lack a core, consisting instead of a denser and denser fluid, predominantly molecular and metallic hydrogen. All the way to the center. Data from the Juno mission showed that Jupiter has a diffuse core that mixes into its mantle, extending for 30–50% of the planet's radius, and comprising heavy elements with a combined mass 725 times the Earth. This mixing process could have arisen during formation, while the planet accreted solids and gases from the surrounding nebula. Alternatively, it could have been caused by an impact from a planet of about 10 Earth masses a few million years after Jupiter's formation, which would have disrupted an originally solid Jovian core. Outside the layer of metallic hydrogen lies a transparent interior atmosphere of hydrogen. At this depth, the pressure and temperature are above molecular hydrogen's critical pressure of 1.3 MPa and critical temperature of 33 K, 240.2 degrees C, 400.3 degree F. In this state, there are no distinct liquid and gas phases. Hydrogen is said to be in a supercritical fluid state. The hydrogen and helium gas extending downward from the cloud layer gradually transitions to a liquid in deeper layers, possibly resembling something akin to an ocean of liquid hydrogen and other supercritical fluids. Physically, the gas gradually becomes hotter and denser as depth increases. Rain-like droplets of helium and neon precipitate downward through the lower atmosphere, depleting the abundance of these elements in the upper atmosphere. Calculations suggest that helium drops separate from metallic hydrogen at a radius of 60,000 kilometers, 37,000 miles, 11,000 kilometers, 6,800 miles, below the cloud tops, and merge again at 50,000 kilometers, 31,000 miles, 22,000 kilometers, 14,000 miles, beneath the clouds. Rainfalls of diamonds have been suggested to occur, as well as on Saturn and the ice giants Uranus and Neptune. The temperature and pressure inside Jupiter increase steadily inward as the heat of planetary formation can only escape by convection. At a surface depth where the atmospheric pressure level is 1 bar, 0.10 MPa, the temperature is around 165 K, 108 degrees C, 163 degree F. The region where supercritical hydrogen changes gradually from a molecular fluid to a metallic fluid spans pressure ranges of 5400 GPa with temperatures of 5,0008, 400 K, 4,738, 130 degrees C, 8,540, 14,660 degree F, respectively. The temperature of Jupiter's diluted core is estimated to be 20,000 K, 19,700 degrees Celsius, 35,500 degrees Fahrenheit, with a pressure of around 4,000 GPa. Time-lapse of Jupiter's cloud system moving over the course of 1 month, photographed during Voyager 1 flyby in 1979. The atmosphere of Jupiter extends to a depth of 3,000 kilometers, 2,000 miles, below the cloud layers. Jupiter is perpetually covered with clouds of ammonia crystals, which may contain ammonium hydrosulfide as well. The clouds are located in the tropopause layer of the atmosphere, forming bands at different latitudes, known as tropical regions. These are subdivided into lighter-hued zones and darker belts. The interactions of these conflicting circulation patterns cause storms and turbulence. Wind speeds of 100 meters per second, 360 kilometers per hour, 220 miles per hour, are common in zonal jet streams. The zones have been observed to vary in width, color, and intensity from year to year, but they have remained stable enough for scientists to name them. The cloud layer is about 50 kilometers, 31 miles, deep, and consists of at least 2 decks of ammonia clouds, a thin clearer region on top with a thick lower deck. There may be a thin layer of water clouds underlying the ammonia clouds, as suggested by flashes of lightning detected in the atmosphere of Jupiter. These electrical discharges can be up to 1,000 times as powerful as lightning on Earth. The water clouds are assumed to generate thunderstorms in the same way as terrestrial thunderstorms, driven by the heat rising from the interior. The Juno mission revealed the presence of shallow lightning which originates from ammonia water clouds relatively high in the atmosphere. These discharges carry mush balls of water ammonia slushes covered in ice, which fall deep into the atmosphere. Upper atmospheric lightning has been observed in Jupiter's upper atmosphere, bright flashes of light that last around 1.4 milliseconds. These are known as elves or sprites and appear blue or pink due to the hydrogen. The orange and brown colors in the clouds of Jupiter are caused by upwelling compounds that change color when they are exposed to ultraviolet light from the sunday. The exact makeup remains uncertain, but the substances are thought to be made up of phosphorus, sulfur, or possibly hydrocarbons. These colorful compounds, known as chromophores, mix with the warmer clouds of the lower deck. The light-colored zones are formed when rising convection cells form crystallizing ammonia that hides the chromophores from view. Jupiter has a low axial tilt, thus making it that the poles always receive less solar radiation than the planet's equatorial region. Convection within the interior of the planet transports energy to the poles, balancing out temperatures at the cloud layer. A well-known feature of Jupiter is the Great Red Spot, a persistent anticyclonic storm located 22 degrees south of the equator. It was first observed in 1831, and possibly as early as 1665. Images by the Hubble Space Telescope have shown two more red spots adjacent to the Great Red Spot. The storm is visible through Earth-based telescopes with an aperture of 12 centimeters or larger. The oval object rotates counterclockwise, with a period of about 6 days. The maximum altitude of this storm is about 8 kilometers, 5 miles, above the surrounding cloud tops. The spot's composition and the source of its red color remain uncertain, although photo-dissociated ammonia reacting with acetylene is a likely explanation. The Great Red Spot is larger than the Earth. Mathematical models suggest that the storm is stable and will be a permanent feature of the planet. However, it has significantly decreased in size since its discovery. Initial observations in the late 1800s showed it to be approximately 41,000 kilometers, 25,500 miles, across. By the time of the Voyager flybys in 1979, the storm had a length of 23,300 kilometers, 14,500 miles, and a width of approximately 13,000 kilometers, 8,000 miles. Hubble observations in 1995 showed it had decreased in size to 20,950 kilometers, 13,020 miles, and observations in 2009 showed the size to be 17,910 kilometers, 11,130 miles. As of 2015, the storm was measured at approximately 16,500 by 10,940 kilometers, 10,250 by 6,800 miles, and was decreasing in length by about 930 kilometers, 580 miles, per year. In October 2021, a Juno flyby mission measured the depth of the Great Red Spot, putting it at around 300-500 kilometers, 193-10 mi. Juno missions show that there are several polar cyclone groups at Jupiter's poles. The northern group contains 9 cyclones, with a large one in the center and 8 others around it, while its southern counterpart also consists of a center vortex but is surrounded by 5 large storms and a single smaller one for a total of 7 storms. These polar structures are caused by the turbulence in Jupiter's atmosphere and can be compared with the hexagon at Saturn's North Pole. In 2000, an atmospheric feature formed in the southern hemisphere that is similar in appearance to the Great Red Spot, but smaller. This was created when smaller, white oval-shaped storms merged to form a single feature. These 3 smaller white ovals were formed in 1939-1940. The merged feature was named Oval BA. It has since increased in intensity and changed from white to red, earning it the nickname Little Red Spot. In April 2017, a great cold spot was discovered in Jupiter's thermosphere at its north pole. This feature is 24,000 kilometers, 15,000 miles, across, 12,000 kilometers, 7,500 miles, wide, and 200 degrees Celsius, 360 degrees Fahrenheit, cooler than surrounding material. While this spot changes form and intensity over the short term, it has maintained its general position in the atmosphere for more than 15 years. It may be a giant vortex similar to the Great Red Spot, and appears to be quasi-stable like the vortices in Earth's thermosphere. This feature may be formed by interactions between charged particles generated from Io and the strong magnetic field of Jupiter, resulting in a redistribution of heat flow. Jupiter's magnetic field is the strongest of any planet in the Solar System, with a dipole moment of 4.170 Gauss, 0.4170 mt, that is tilted at an angle of 10.31 degrees to the pole of rotation. The surface magnetic field strength varies from 2 Gauss, 0.20 mt, up to 20 Gauss, 2.0 mt. This field is thought to be generated by eddy currents swirling movements of conducting materials within the liquid, metallic hydrogen core. At about 75 Jupiter radii from the planet, the interaction of the magnetosphere with the solar wind generates a bow shock. Surrounding Jupiter's magnetosphere is a magnetopause, located at the inner edge of a magnetosheath, a region between it and the bow shock. The solar wind interacts with these regions, elongating the magnetosphere on Jupiter's lee side and extending it outward until it nearly reaches the orbit of Saturn. The 4 largest moons of Jupiter all orbit within the magnetosphere, which protects them from solar wind. The volcanoes on the moon Io emit large amounts of sulfur dioxide, forming a gas torus along its orbit. The gas is ionized in Jupiter's magnetosphere, producing sulfur and oxygen ions. They, together with hydrogen ions originating from the atmosphere of Jupiter, form a plasma sheet in Jupiter's equatorial plane. The plasma in the sheet CO rotates with the planet, causing deformation of the dipole magnetic field into that of a magnetodisk. Electrons within the plasma sheet generate a strong radio signature, with short, superimposed bursts in the range of 0.630 MHz that are detectable from Earth with consumer-grade shortwave radio receivers. As Io moves through this torus, the interaction generates Alfvén waves that carry ionized matter into the polar regions of Jupiter. As a result, radio waves are generated through a cyclotron maser mechanism, and the energy is transmitted out along a cone-shaped surface. When Earth intersects this cone, the radio emissions from Jupiter can exceed the radio output of the Sunday. Jupiter has a faint planetary ring system composed of 3 main segments, an inner torus of particles known as the halo, a relatively bright main ring, and an outer gossamer ring. These rings appear to be made of dust, whereas Saturn's rings are made of ice. 65 The main ring is most likely made out of material ejected from the satellites Adraste and Métis, which is drawn into Jupiter because of the planet's strong gravitational influence. New material is added by additional impacts. In a similar way, the moons Thebe and Amalthea are believed to produce the 2 distinct components of the dusty gossamer ring. There is evidence of a 4th ring that may consist of collisional debris from Amalthea that is strung along the same moon's orbit. Jupiter is the only planet whose barycenter with the Sun lies outside the volume of the Sun, though by only 7% of the Sun's radius. The average distance between Jupiter and the Sun is 778 million km, 5.20, and it completes an orbit every 11.86 years. This is approximately 2/5 the orbital period of Saturn, forming a near-orbital resonance. The orbital plane of Jupiter is inclined 1.30 degrees compared to Earth. Because the eccentricity of its orbit is 0.049, Jupiter is slightly over 75 million km nearer the Sun at perihelion than aphelion. This low eccentricity is at odds with exoplanet discoveries, which have revealed Jupiter-sized planets with very high eccentricities. Models suggest this may be due to there being only 2 giant planets in our solar system, as the presence of a third or more giant planets tends to induce larger eccentricities. The axial tilt of Jupiter is relatively small, only 3.13 degrees, so its seasons are insignificant compared to those of Earth and Mars. Jupiter's rotation is the fastest of all the solar system's planets, completing a rotation on its axis in slightly less than 10 hours. This creates an equatorial bulge easily seen through an amateur telescope. Because Jupiter is not a solid body, its upper atmosphere undergoes differential rotation. The rotation of Jupiter's polar atmosphere is about 5 minutes longer than that of the equatorial atmosphere. The planet is an oblate spheroid, meaning that the diameter across its equator is longer than the diameter measured between its poles. On Jupiter, the equatorial diameter is 9,276 kilometers, 5,764 miles, longer than the polar diameter. 3 systems are used as frames of reference for tracking planetary rotation, particularly when graphing the motion of atmospheric features. System I applies to latitudes from 7 degrees north to 7 degrees south. Its period is the planet's shortest, at 9 hours 50 minutes 30.0 s. System 2 applies at latitudes north and south of these. Its period is 9 hours 55 minutes 40.6 s. System 3 was defined by radio astronomers and corresponds to the rotation of the planet's magnetosphere. Its period is Jupiter's official rotation. Jupiter is the 5th planet from the Sun and the largest in the solar system. It is a gas giant with a mass more than 2.5 times that of all the other planets in the solar system combined, and slightly less. Saturn is the 6th planet from the Sun and the 2nd largest in the solar system, after Jupiter. It is a gas giant with an average radius of about 9.5 times that of Earth. It has only 1/8 the average density of Earth, but is over 95 times more massive. Saturn's interior is thought to be composed of a rocky core, surrounded by a deep layer of metallic hydrogen, an intermediate layer of liquid hydrogen and liquid helium, and finally, a gaseous outer layer. Saturn has a pale yellow hue due to ammonia crystals in its upper atmosphere. An electrical current within the metallic hydrogen layer is thought to give rise to Saturn's planetary magnetic field, which is weaker than Earth's, but which has a magnetic moment 580 times that of Earth due to Saturn's larger size. Saturn's magnetic field strength is around 1/20th of Jupiter's. The outer atmosphere is generally bland and lacking in contrast, although long-lived features can appear. Wind speeds on Saturn can reach 1,800 km per hour, 1,100 miles per hour. The planet has a prominent ring system, which is composed mainly of ice particles, with a smaller amount of rocky debris and dust. At least 146 moons are known to orbit the planet, of which 63 are officially named. This does not include the hundreds of moonlets in its rings. Titan, Saturn's largest moon and the 2nd largest in the solar system, is larger, while less massive, than the planet Mercury and is the only moon in the solar system to have a substantial atmosphere. Saturn is a gas giant composed predominantly of hydrogen and helium. It lacks a definite surface, though it is likely to have a solid core. Saturn's rotation causes it to have the shape of an oblate spheroid, that is, it is flattened at the poles and bulges at its equator. Its equatorial radius is more than 10% larger than its polar radius, 60,268 km versus 54,364 km. Jupiter, Uranus, and Neptune, the other giant planets in the solar system, are also oblate but to a lesser extent. The combination of the bulge and rotation rate means that the effective surface gravity along the equator, 8.96 m/s2, is 74% of what it is at the poles and is lower than the surface gravity of Earth. However, the equatorial escape velocity of nearly 36 km per second is much higher than that of Earth. Saturn is the only planet of the solar system that is less dense than water, about 30% less. Although Saturn's core is considerably denser than water, the average specific density of the planet is 0.69 g/cm3 due to the atmosphere. Jupiter has 318 times Earth's mass, and Saturn is 95 times Earth's mass. Together, Jupiter and Saturn hold 92% of the total planetary mass in the solar system. Despite consisting mostly of hydrogen and helium, most of Saturn's mass is not in the gas phase, because hydrogen becomes a non-ideal liquid when the density is above 0.01 g/cm3, which is reached at a radius containing 99.9% of Saturn's mass. The temperature, pressure, and density inside Saturn all rise steadily toward the core, which causes hydrogen to be a metal in the deeper layers. Standard planetary models suggest that the interior of Saturn is similar to that of Jupiter, having a small rocky core surrounded by hydrogen and helium, with trace amounts of various volatiles. Analysis of the distortion shows that Saturn is substantially more centrally condensed than Jupiter and therefore contains a significantly larger amount of material denser than hydrogen near its center. Saturn's central regions contain about 50% hydrogen by mass, while Jupiter's contain approximately 67% hydrogen. This core is similar in composition to Earth, but is more dense. The examination of Saturn's gravitational moment, in combination with physical models of the interior, has allowed constraints to be placed on the mass of Saturn's core. In 2004, scientists estimated that the core must be 922 times the mass of Earth, which corresponds to a diameter of about 25,000 kilometers. However, measurements of Saturn's rings suggest a much more diffuse core with a mass equal to about 17 Earths and a radius equal to around 60% of Saturn's entire radius. This is surrounded by a thicker liquid metallic hydrogen layer, followed by a liquid layer of helium-saturated molecular hydrogen that gradually transitions to a gas with increasing altitude. The outermost layer spans 1,000 kilometers and consists of gas. Saturn has a hot interior, reaching 11,700 degrees Celsius at its core, and radiates 2.5 times more energy into space than it receives from the Sunday. Jupiter's thermal energy is generated by the Kelvin-Helmholtz mechanism of slow gravitational compression, but such a process alone may not be sufficient to explain heat production for Saturn, because it is less massive. An alternative or additional mechanism may be the generation of heat through the raining out of droplets of helium deep in Saturn's interior. As the droplets descend through the lower density hydrogen, the process releases heat by friction and leaves Saturn's outer layers depleted of helium. These descending droplets may have accumulated into a helium shell surrounding the core. Rainfalls of diamonds have been suggested to occur within Saturn, as well as in Jupiter and ice giants Uranus and Neptune. The outer atmosphere of Saturn contains 96.3% molecular hydrogen and 3.25% helium by volume. The proportion of helium is significantly deficient compared to the abundance of this element in the Sunday. The quantity of elements heavier than helium, metallicity, is not known precisely, but the proportions are assumed to match the primordial abundances from the formation of the Solar System. The total mass of these heavier elements is estimated to be 1931 times the mass of Earth, with a significant fraction located in Saturn's core region. Trace amounts of ammonia, acetylene, ethane, propane, phosphine, and methane have been detected in Saturn's atmosphere. The upper clouds are composed of ammonia crystals, while the lower-level clouds appear to consist of either ammonium hydrosulfide, NH4SH, or water. Ultraviolet radiation from the Sun causes methane photolysis in the upper atmosphere, leading to a series of hydrocarbon chemical reactions with the resulting products being carried downward by eddies and diffusion. This photochemical cycle is modulated by Saturn's annual seasonal cycle. Cassini observed a series of cloud features found in northern latitudes, nicknamed the String of Pearls. These features are cloud clearings that reside in deeper cloud layers. Saturn's atmosphere exhibits a banded pattern similar to Jupiter's, but Saturn's bands are much fainter and are much wider near the equator. The nomenclature used to describe these bands is the same as on Jupiter. Saturn's finer cloud patterns were not observed until the flybys of the Voyager spacecraft during the 1980s. Since then, Earth-based telescopy has improved to the point where regular observations can be made. The composition of the clouds varies with depth and increasing pressure. In the upper cloud layers, with temperatures in the range of 100–160 K and pressures extending between 0.52 bar, the clouds consist of ammonia ice. Water ice clouds begin at a level where the pressure is about 2.5 bar and extend down to 9.5 bar, where temperatures range from 185 to 270 K. Intermixed in this layer is a band of ammonium hydrosulfide ice, lying in the pressure range 36 bar with temperatures of 190 to 35 K. Finally, the lower layers, where pressures are between 10 and 20 bar and temperatures are 270–330 K, contains a region of water droplets with ammonia in aqueous solution. Saturn's usually bland atmosphere occasionally exhibits long-lived ovals and other features common on Jupiter. In 1990, the Hubble Space Telescope imaged an enormous white cloud near Saturn's equator that was not present during the Voyager encounters, and in 1994 another smaller storm was observed. The 1990 storm was an example of a great white spot, a short-lived phenomenon that occurs once every Saturnian year, roughly every 30 Earth years, around the time of the Northern Hemisphere's summer solstice. Previous great white spots were observed in 1876, 1903, 1933, and 1960, with the 1933 storm being the best observed. The latest giant storm was observed in 2010. In 2015, researchers used Very Large Array Telescope to study Saturnian atmosphere, and reported that they found long-lasting signatures of all mid-latitude giant storms, a mixture of equatorial storms up to hundreds of years old, and potentially an unreported older storm at 70° N. The winds on Saturn are the second fastest among the Solar System's planets, after Neptune's. Voyager data indicate peak easterly winds of 500 m/s, 1,800 km per hour. In images from the Cassini spacecraft during 2007, Saturn's northern hemisphere displayed a bright blue hue, similar to Uranus. The color was most likely caused by Rayleigh scattering. Thermography has shown that Saturn's south pole has a warm polar vortex, the only known example of such a phenomenon in the Solar System. Whereas temperatures on Saturn are normally 185° C, temperatures on the vortex often reach as high as 122° C, suspected to be the warmest spot on Saturn. A persisting hexagonal wave pattern around the north polar vortex in the atmosphere at about 78° north was first noted in the Voyager images. The sides of the hexagon are each about 14,500 kilometers, 9,000 miles, long, which is longer than the diameter of the Earth. The entire structure rotates with a period of 10 hours 39 minutes and 24 seconds, the same period as that of the planet's radio emissions, which is assumed to be equal to the period of rotation of Saturn's interior. The hexagonal feature does not shift in longitude like the other clouds in the visible atmosphere. The pattern's origin is a matter of much speculation. Most scientists think it is a standing wave pattern in the atmosphere. Polygonal shapes have been replicated in the laboratory through differential rotation of fluids. HST imaging of the south polar region indicates the presence of a jet stream, but no strong polar vortex nor any hexagonal standing wave. NASA reported in November 2006 that Cassini had observed a hurricane-like storm locked to the South Pole that had a clearly defined eyewall. Eyewall clouds had not previously been seen on any planet other than Earth. For example, images from the Galileo spacecraft did not show an eyewall in the Great Red Spot of Jupiter. The South Pole storm may have been present for billions of years. This vortex is comparable to the size of Earth, and it has winds of 550 km per hour. Saturn has an intrinsic magnetic field that has a simple, symmetric shape, a magnetic dipole. Its strength at the equator 0.2 Gauss, T, is approximately 1/20th of that of the field around Jupiter and slightly weaker than Earth's magnetic field. As a result, Saturn's magnetosphere is much smaller than Jupiter's. When Voyager 2 entered the magnetosphere, the solar wind pressure was high and the magnetosphere extended only 19 Saturn radii, or 1.1 million km, 712,000 miles, although it enlarged within several hours, and remained so for about 3 days. Most probably, the magnetic field is generated similarly to that of Jupiter by currents in the liquid metallic hydrogen layer called a metallic hydrogen dynamo. This magnetosphere is efficient at deflecting the solar wind particles from the Sunday. The Moon Titan orbits within the outer part of Saturn's magnetosphere and contributes plasma from the ionized particles in Titan's outer atmosphere. Saturn's magnetosphere, like Earth's. The average distance between Saturn and the Sun is over 1.4 billion kilometers, 90. With an average orbital speed of 9.68 kilometers per second, it takes Saturn 10,759 Earth days, or about 29 plus 12 years, to finish one revolution around the Sunday. As a consequence, it forms a near 5:2 mean motion resonance with Jupiter. The elliptical orbit of Saturn is inclined 2.48 degrees relative to the orbital plane of the Earth. The perihelion and aphelion distances are, respectively, 9.195 and 9.9570, on average. The visible features on Saturn rotate at different rates depending on latitude, and multiple rotation periods have been assigned to various regions, as in Jupiter's case. Astronomers use three different systems for specifying the rotation rate of Saturn. System I has a period of 10 hours 14 minutes and 0 seconds, 844.3 degrees/d, and encompasses the equatorial zone, the south equatorial belt, and the north equatorial belt. The polar regions are considered to have rotation rates similar to System I. All other Saturnian latitudes, excluding the north and south polar regions, are indicated as System II and have been assigned a rotation period of 10 hours 38 minutes 25.4 s, 810.76 degrees/d. System III refers to Saturn's internal rotation rate. Based on radio emissions from the planet detected by Voyager 1 and Voyager 2, System III has a rotation period of 10 hours 39 minutes 22.4 s, 810.8 degrees/d. System III has largely superseded System II. A precise value for the rotation period of the interior remains elusive. While approaching Saturn in 2004, Cassini found that the radio rotation period of Saturn had increased appreciably, to approximately 10 hours 45 minutes and 45 seconds plus or minus 30 SIXS. An estimate of Saturn's rotation, as an indicated rotation rate for Saturn as a whole, based on a compilation of various measurements from the Cassini, Voyager, and Pioneer probes is 10 hours 32 minutes and 35 seconds. Studies of the planet's C-ring yield a rotation period of 10 hours 33 minutes and 38 seconds plus 1 minute and 52 seconds. 1 minute and 19 seconds. In March 2007, it was found that the variation in radio emissions from the planet did not match Saturn's rotation rate. This variance may be caused by geyser activity on Saturn's moon Enceladus. The water vapor emitted into Saturn's orbit by this activity becomes charged and creates a drag upon Saturn's magnetic field, slowing its rotation slightly relative to the rotation of the planet. An apparent oddity for Saturn is that it does not have any known Trojan asteroids. These are minor planets that orbit the Sun at the stable Lagrangian points, designated L4 and L5, located at 60 degrees angles to the planet along its orbit. Trojan asteroids have been discovered for Mars, Jupiter, Uranus, and Neptune. Orbital resonance mechanisms, including secular resonance, are believed to be the cause of the missing Saturnian Trojans. Saturn has 146 known moons, 63 of which have formal names. It is estimated that there are other 100 plus or minus 30 outer irregular moons larger than 3 kilometers, 2 miles, in diameter. In addition, there is evidence of dozens to hundreds of moonlets with diameters of 4,500 meters in Saturn's rings, which are not considered to be true moons. Titan, the largest moon, comprises more than 90% of the mass in orbit around Saturn, including the rings. Saturn's second largest moon, Rhea, may have a tenuous ring system of its own, along with a tenuous atmosphere. Many of the other moons are small, 131 are less than 50 kilometers in diameter. Traditionally, most of Saturn's moons have been named after titans of Greek mythology. Titan is the only satellite in the solar system with a major atmosphere, in which a complex organic chemistry occurs. It is the only satellite with hydrocarbon lakes. On June 6, 2013, scientists at the IAACSIC reported the detection of polycyclic aromatic hydrocarbons in the upper atmosphere of Titan, a possible precursor for life. On June 23, 2014, NASA claimed to have strong evidence that nitrogen in the atmosphere of Titan came from materials in the Oort cloud, associated with comets, and not from the materials that formed Saturn in earlier times. Saturn's moon Enceladus, which seems similar in chemical makeup to comets, has often been regarded as a potential habitat for microbial life. Evidence of this possibility includes the satellite's salt-rich particles having an ocean-like composition that indicates most of Enceladus's expelled ice comes from the evaporation of liquid salt water. A 2015 flyby by Cassini through a plume on Enceladus found most of the ingredients to sustain life forms that live by methanogenesis. In April 2014, NASA scientists reported the possible beginning of a new moon within the A-ring, which was imaged by Cassini on April 15, 2013. Saturn is probably best known for the system of planetary rings that makes it visually unique. The rings extend from 6,630 to 120,700 kilometers, 4,120 to 75,000 miles, outward from Saturn's equator and average approximately 20 meters, 66 feet, in thickness. They are composed predominantly of water ice, with trace amounts of tholin impurities and a peppered coating of approximately 7% amorphous carbon. The particles that make up the rings range in size from specks of dust up to 10 m. While the other gas giants also have ring systems, Saturn's is the largest and most visible. There are two main hypotheses regarding the origin of the rings. One hypothesis is that the rings are remnants of a destroyed moon of Saturn, for which a research team at MIT has proposed the name chrysalis. The second hypothesis is that the rings are left over from the original nebular material from which Saturn was formed. Some ice in the E-ring comes from the moon Enceladus's geysers. The water abundance of the rings varies radially, with the outermost ring A being the most pure in ice water. This abundance variance may be explained by meteor bombardment. Beyond the main rings, at a distance of 12 million km from the planet is the sparse Phoebe ring. It is tilted at an angle of 27 degrees to the other rings and, like Phoebe, orbits in retrograde fashion. Some of the moons of Saturn, including Pandora and Prometheus, act as shepherd moons to confine the rings and prevent them from spreading out. Pan and Atlas cause weak, linear density waves in Saturn's rings that have yielded more reliable calculations of their masses. Saturn is the sixth planet from the Sun and the second largest in the Solar System, after Jupiter. It is a gas. Uranus is the seventh planet from the Sun and is a gaseous cyan ice giant. Most of the planet is made of water, ammonia, and methane in a supercritical phase of matter, which in astronomy is called ice or volatiles. The planet's atmosphere has a complex layered cloud structure and has the lowest minimum temperature of 49 K, 224 degrees C, 371 degree F, out of all solar system's planets. It has a marked axial tilt of 97.8 degrees with a retrograde rotation rate of 17 hours. This means that in an 84 Earth years orbital period around the Sun, its poles get around 42 years of continuous sunlight, followed by 42 years of continuous darkness. Uranus has the third largest diameter and fourth largest mass among the solar system's planets. Based on current models, inside its volatile mantle layer is a rocky core, and surrounding it is a thick hydrogen and helium atmosphere. Trace amounts of hydrocarbons, thought to be produced via hydrolysis, and carbon monoxide along with carbon dioxide, thought to have been originated from comets, have been detected in the upper atmosphere. There are many unexplained climate phenomena in Uranus's atmosphere, such as its peak wind speed of 900 km per hour, 560 miles per hour, variations in its polar cap and its erratic cloud formation. The planet also has very low internal heat compared to other giant planets, which is still unexplained. Like the other giant planets, Uranus has a ring system, orbiting natural satellites in a magnetosphere. Its ring system is extremely dark, with only about 2% of the incoming light reflected, and contains the known 13 inner moons. Further out are the larger 5 major moons of the planet, Miranda, Ariel, Umbriel, Titania, and Oberon, and orbiting at much greater distance from Uranus are the known 9 irregular moons. The planet's magnetosphere is highly asymmetric and has many charged particles, which may cause the darkening of its rings and moons. Uranus is visible to the naked eye, but it is very dim and was not classified as a planet until 1781, when it was first observed by William Herschel. About 7 decades after its discovery, consensus was reached that the planet be named from the Greek god Uranus, Ouranos, one of the Greek primordial deities. As of 2023, it was visited up close only once when in 1986 the Voyager 2 probe flew by the planet. Though nowadays it can be resolved and observed by telescopes, there is much desire to revisit the planet, as shown by Planetary Science Decadal Survey's decision to make the proposed Uranus orbiter and probe mission a top priority in the 2023-2032 survey. Like the classical planets, Uranus is visible to the naked eye, but it was never recognized as a planet by ancient observers because of its dimness and slow orbit. Sir William Herschel first observed Uranus on March 13, 1781, leading to its discovery as a planet, expanding the known boundaries of the solar system for the first time in history and making Uranus the first planet classified as such with the aid of a telescope. Uranus had been observed on many occasions before its recognition as a planet, but it was generally mistaken for a star. Possibly the earliest known observation was by Hipparchus, who in 128 BC might have recorded it as a star for his star catalogue that was later incorporated into Ptolemy's Almagest. The earliest definite sighting was in 1690, when John Flamsteed observed it at least 6 times, cataloguing it as 34 Tauri. The French astronomer Pierre-Charles Lemonnier observed Uranus at least 12 times between 1750 and 1769, including on 4 consecutive nights. Sir William Herschel observed Uranus on March 13, 1781 from the garden of his house at 19 New King Street in Bath, Somerset, England, now the Herschel Museum of Astronomy, and initially reported it, on April 26, 1781, as a comet. With a homemade 6.2-inch reflecting telescope, Herschel engaged in a series of observations on the parallax of the fixed stars. Herschel recorded in his journal, in the quartile near Zeta Tauri, either nebulous star or perhaps a comet. On March 17 he noted, "I looked for the comet or nebulous star and found that it is a comet, for it has changed its place." When he presented his discovery to the Royal Society, he continued to assert that he had found a comet, but also implicitly compared it to a planet. "The power I had on when I first saw the comet was 227. From experience I know that the diameters of the fixed stars are not proportionally magnified with higher powers, as planets are, therefore I now put the powers at 460 and 932, and found that the diameter of the comet increased in proportion to the power, as it ought to be, on the supposition of its not being a fixed star, while the diameters of the stars to which I compared it were not increased in the same ratio. Moreover, the comet being magnified much beyond what its light would admit of, appeared hazy and ill-defined with these great powers, while the stars preserved that luster and distinctness which from many thousand observations I knew they would retain. The sequel has shown that my surmises were well founded, this proving to be the comet we have lately observed." Herschel notified the astronomer Royal Neville Maskelyne of his discovery and received this flummoxed reply from him on April 23, 1781, "I don't know what to call it. It is as likely to be a regular planet moving in an orbit nearly circular to the Sun as a comet moving in a very eccentric ellipsis. I have not yet seen any coma or tail to it." Although Herschel continued to describe his new object as a comet, other astronomers had already begun to suspect otherwise. Finnish-Swedish astronomer Anders Johan Lexell, working in Russia, was the first to compute the orbit of the new object. Its nearly circular orbit led him to the conclusion that it was a planet rather than a comet. Berlin astronomer Johann Elert Bode described Herschel's discovery as a moving star that can be deemed a hitherto unknown planet-like object circulating beyond the orbit of Saturn. Bode concluded that its near-circular orbit was more like a planet's than a comet's. The object was soon universally accepted as a new planet. By 1783, Herschel acknowledged this to Royal Society President Joseph Banks. "By the observation of the most eminent astronomers in Europe it appears that the new star, which I had the honor of pointing out to them in March 1781, is a primary planet of our solar system. In recognition of his achievement, King George III gave Herschel an annual stipend of £200, equivalent to £26,000 in 2021, on condition that he moved to Windsor so that the royal family could look through his telescopes. The name Uranus references the ancient Greek deity of the sky Uranus, ancient Greek, Omicron Rho Alpha Nu, known as Cyalis in Roman mythology, the father of Cronus, Saturn, and grandfather of Zeus, Jupiter, which was rendered as Uranus in Latin, IPA, Urans. It is the only one of the 8 planets whose English name derives from a figure of Greek mythology. The adjectival form of Uranus is Uranian. The pronunciation of the name Uranus preferred among astronomers is /jrns/yoorns, with stress on the first syllable as in Latin Uranus, in contrast to /jren/urans, with stress on the second syllable and a long a, though both are considered acceptable. Consensus on the name was not reached until almost 70 years after the planet's discovery. During the original discussions following discovery, Maskelyne asked Herschel to do the astronomical world the favor to give a name to your planet, which is entirely your own, and which we are so much obliged to you for the discovery of. In response to Maskelyne's request, Herschel decided to name the object Georgium Sidus, George's star, or the Georgian planet in honor of his new patron, King George III. He explained this decision in a letter to Joseph Banks. In the fabulous ages of ancient times the appellations of Mercury, Venus, Mars, Jupiter, and Saturn were given to the planets, as being the names of their principal heroes and divinities. In the present more philosophical era it would hardly be allowable to have recourse to the same method and call it Juno, Pallas, Apollo, or Minerva, for a name to our new heavenly body. The first consideration of any particular event, or remarkable incident, seems to be its chronology, if in any future age it should be asked, when this last found planet was discovered. It would be a very satisfactory answer to say, in the reign of King George III. Herschel's proposed name was not popular outside Britain and Hanover, and alternatives were soon proposed. Astronomer Jerome Lalande proposed that it be named Herschel in honor of its discoverer. Swedish astronomer Erik Prosperin proposed the names Astrea, Cybele, now the names of asteroids, and Neptune, which would become the name of the next planet to be discovered. The name was supported by other astronomers who liked the idea to commemorate the victories of the British Royal Naval Fleet in the course of the American Revolutionary War by calling the new planet even Neptune George III or Neptune Great Britain, a compromise Lexell suggested as well. Daniel Bernoulli suggested Hypercranius and Transaturnus. George Lichtenberg from Göttingen suggested Ostrat, a goddess mentioned by Ovid, but who is traditionally associated with Virgo. The name Minerva was also proposed. In a March 1782 treatise, Bode proposed Uranus, the Latinized version of the Greek god of the sky, Uranus. Bode argued that the name should follow the mythology so as not to stand out as different from the other planets, and that Uranus was an appropriate name as the father of the first generation of the Titans. He also noted that elegance of the name in that just as Saturn was the father of Jupiter, the new planet should be named after the father of Saturn. Bode was however apparently unaware that Uranus was only the Latinized form of the titular deity, and his Roman equivalent was Cyalis. In 1789, Bode's Royal Academy colleague Martin Klaproth named his newly discovered element uranium in support of Bode's choice. Ultimately, Bode's suggestion became the most widely used, and became universal in 1850 when Nautical Almanac Office, the final holdout, switched from using Georgium Sidus to Uranus. Uranus has 2 astronomical symbols. The first to be proposed, was proposed by Johann Gottfried Kohler at Bode's request in 1782. Kohler suggested that the new planet be given the symbol for platinum, which had been described scientifically only 30 years before. As there was no alchemical symbol for platinum, he suggested a combination of the planetary metal symbols, gold, and iron, as platinum, or white gold, is found mixed with iron. Bode thought that an upright orientation fit better with the symbols for the other planets while remaining distinct. This symbol predominates in modern astronomical use in the rare cases that symbols are used at all. The second symbol, H, was suggested by Lalande in 1784. In a letter to Herschel, Lalande described it as un globe surmonté par la première lettre de votre nom, a globe surmounted by the first letter of your surname. The second symbol is nearly universal in astrology. Uranus is called by a variety of names in other languages. Uranus's name is literally translated as the Sky King Star in Chinese, Japanese, Korean, and Vietnamese, Sao Tien Vng. In Thai, its official name is Deo Uranat, as in English. Its other name in Thai is Deo Maruat Teu, Star of Mdayu, after the Sanskrit word for death, Mrtyu. In Mongolian, its name is Tentrian Van, translated as King of the Sky, reflecting its namesake god's role as the ruler of the heavens. In Hawaiian, its name is Helikala, the Hawaiian rendering of the name Herschel in Maori, its name is Waitrangi. It is argued that the differences between the ice giants and the gas giants arise from their formation history. The solar system is hypothesized to have formed from a rotating disk of gas and dust known as the Presola Nebula. Much of the nebula's gas, primarily hydrogen and helium, formed the Sun, and the dust grains collected together to form the first protoplanets. As the planets grew, some of them eventually accreted enough matter for their gravity to hold onto the nebula's leftover gas. The more gas they held onto, the larger they became, the larger they became, the more gas they held onto until a critical point was reached, and their size began to increase exponentially. The ice giants, with only a few Earth masses of nebular gas, never reached that critical point. Recent simulations of planetary migration have suggested that both ice giants formed closer to the Sun than their present positions, and moved outwards after formation, the NICE model. Uranus orbits the Sun once every 84 years. In 2033, the planet will have made its third complete orbit around the Sun since being discovered in 1781. The planet has returned to the point of its discovery northeast of Zeta Tauri twice since then, on March 25, 1865 and March 29, 1949. Uranus will return to this location again on April 3, 2033. Its average distance from the Sun is roughly 20.03 billion km, 2 billion mi. The difference between its minimum and maximum distance from the Sun is 1.80, larger than that of any other planet, though not as large as that of dwarf planet Pluto. The intensity of sunlight varies inversely with the square of distance, and so on Uranus, at about 20 times the distance from the Sun compared to Earth, it is about 1/400 the intensity of light on Earth. The orbital elements of Uranus were first calculated in 1783 by Pierre-Simon Laplace. With time, discrepancies began to appear between predicted and observed orbits, and in 1841, John Couch Adams first proposed that the differences might be due to the gravitational tug of an unseen planet. In 1845, Urbain Le Verrier began his own independent research into Uranus's orbit. On September 23, 1846, Johann Gottfried Galle located a new planet, later named Neptune, at nearly the position predicted by Le Verrier. The rotational period of the interior of Uranus is 17 hours, 14 minutes. As on all giant planets, its upper atmosphere experiences strong winds in the direction of rotation. At some latitudes, such as about 60 degrees south, visible features of the atmosphere move much faster, making a full rotation in as little as 14 hours. Simulated Earth view of Uranus from 1986 to 2030, from southern summer solstice in 1986 to equinox in 2007 and northern summer solstice in 2028. The Uranian axis of rotation is approximately parallel to the plane of the Solar System, with an axial tilt of 97.77 degrees, as defined by prograde rotation. This gives it seasonal changes completely unlike those of the other planets. Pluto and the protoplanet asteroid 2 Pallas also have extreme axial tilts. Near the solstice, one pole faces the Sun continuously and the other faces away, with only a narrow strip around the equator experiencing a rapid day-night cycle, with the Sun low over the horizon. On the other side of Uranus's orbit, the orientation of the poles towards the Sun is reversed. Each pole gets around 42 years of continuous sunlight, followed by 42 years of darkness. Near the time of the equinoxes, the Sun faces the equator of Uranus, giving a period of day-night cycles similar to those seen on most of the other planets. One result of this axis orientation is that, averaged over the Uranian year, the near-polar regions of Uranus receive a greater energy input from the Sun than its equatorial regions. Nevertheless, Uranus is hotter at its equator than at its poles. The underlying mechanism that causes this is unknown. The reason for Uranus's unusual axial tilt is also not known with certainty, but the usual speculation is that during the formation of the Solar System, an Earth-sized protoplanet collided with Uranus, causing the skewed orientation. Research by Jacob K. Gares of Durham University suggests that the tilt resulted from a rock larger than Earth crashing into the planet 3 to 4 billion years ago. Uranus's south pole was pointed almost directly at the Sun at the time of Voyager 2's flyby in 1986. The labeling of this pole as south uses the definition currently endorsed by the International Astronomical Union, namely that the north pole of a planet or satellite is the pole that points above the invariable plane of the Solar System, regardless of the direction the planet is spinning. A different convention is sometimes used, in which a body's north and south poles are defined according to the right-hand rule in relation to the direction of rotation. The mean apparent magnitude of Uranus is 5.68 with a standard deviation of 0.17, while the extremes are 5.38 and 6.03. This range of brightness is near the limit of naked eye visibility. Much of the variability is dependent upon the planetary latitudes being illuminated from the Sun and viewed from the Earth. Its angular diameter is between 3.4 and 3.7 arcseconds, compared with 16 to 20 arcseconds for Saturn and 32 to 45 arcseconds for Jupiter. At opposition, Uranus is visible to the naked eye in dark skies, and becomes an easy target even in urban conditions with binoculars. On larger amateur telescopes with an objective diameter of between 15 and 23 centimeters, Uranus appears as a pale cyan disk with distinct limb darkening. With a large telescope of 25 centimeters or wider, cloud patterns, as well as some of the larger satellites, such as Titania and Oberon, may be visible. Uranus's mass is roughly 14.5 times that of Earth, making it the least massive of the giant planets. Its diameter is slightly larger than Neptune's at roughly 4 times that of Earth. A resulting density of 1.27 g/cm3 makes Uranus the second least dense planet, after Saturn. This value indicates that it is made primarily of various ices, such as water, ammonia, and methane. The total mass of ice in Uranus's interior is not precisely known, because different figures emerge depending on the model chosen. It must be between 9.3 and 13.5 Earth masses. Hydrogen and helium constitute only a small part of the total, with between 0.5 and 1.5 Earth masses. The remainder of the non-ice mass, 0.5 to 3.7 Earth masses, is accounted for by rocky material. The standard model of Uranus's structure is that it consists of 3 layers, a rocky, silicate/iron-nickel, core in the center, an icy mantle in the middle and an outer gaseous hydrogen/helium envelope. The core is relatively small, with a mass of only 0.55 Earth masses and a radius less than 20% of Uranus. The mantle comprises its bulk, with around 13.4 Earth masses, and the upper atmosphere is relatively insubstantial, weighing about 0.5 Earth masses and extending for the last 20% of Uranus's radius. Uranus's core density is around 9 g/cm3, with a pressure in the center of 8 million bars, 800 GPa, and a temperature of about 5000 K. The ice mantle is not in fact composed of ice in the conventional sense, but of a hot and dense fluid consisting of water, ammonia, and other volatiles. This fluid, which has a high electrical conductivity, is sometimes called a water-ammonia ocean. The extreme pressure and temperature deep within Uranus may break up the methane molecules, with the carbon atoms condensing into crystals of diamond that rain down through the mantle like hailstones. This phenomenon is similar to diamond rains that are theorized by scientists to exist on Jupiter, Saturn, and Neptune. Very high-pressure experiments at the Lawrence Livermore National Laboratory suggest that the base of the mantle may comprise an ocean of metallic liquid carbon, perhaps with floating solid diamond bergs. The bulk compositions of Uranus and Neptune are different from those of Jupiter and Saturn, with ice dominating over gases, hence justifying their separate classification as ice giants. There may be a layer of ionic water where the water molecules break down into a soup of hydrogen and oxygen ions, and deeper down superionic water in which the oxygen crystallizes but the hydrogen ions move freely within the oxygen lattice. Although the model considered above is reasonably standard, it is not unique. Other models also satisfy observations. For instance, if substantial amounts of hydrogen and rocky material are mixed in the ice mantle, the total mass of ices in the interior will be lower, and, correspondingly, the total mass of rocks and hydrogen will be higher. Presently available data does not allow a scientific determination of which model is correct. The fluid interior structure of Uranus means that it has no solid surface. The gaseous atmosphere gradually transitions into the internal liquid layers. For the sake of convenience, a revolving oblate spheroid set at the point at which atmospheric pressure equals 1 bar, 100 kPa, is conditionally designated as a surface. It has equatorial and polar radii of 25,559 plus or minus 4 kilometers, 15,881.6 plus or minus 2.5 miles, and 24,973 plus or minus 20 kilometers, 15,518 plus or minus 12 miles, respectively. This surface is used throughout this article as a zero point for altitudes. Uranus's internal heat appears markedly lower than that of the other giant planets. In astronomical terms, it has a low thermal flux. Why Uranus's internal temperature is so low is still not understood. Neptune, which is Uranus's near twin in size and composition, radiates 2.61 times as much energy into space as it receives from the Sun, but Uranus radiates hardly any excess heat at all. The total power radiated by Uranus in the far infrared, i.e. heat, part of the spectrum is 1.06 plus or minus 0.08 times the solar energy absorbed in its atmosphere. Uranus's heat flux is only 0.042 plus or minus 0.047 W/m2, which is lower than the internal heat flux of Earth of about 0.075 W/m2. The lowest temperature recorded in Uranus's tropopause is 49 K, 224.2 degrees C, 371.5 degree F, making Uranus the coldest planet in the solar system. One of the hypotheses for this discrepancy suggests that when Uranus was hit by a supermassive impactor, which caused it to expel most of its primordial heat, it was left with a depleted core temperature. This impact hypothesis is also used in some attempts to explain the planet's axial tilt. Another hypothesis is that some form of barrier exists in Uranus's upper layers that prevents the core's heat from reaching the surface. For example, convection may take place in a set of compositionally different layers, which may inhibit upward heat transport. Perhaps double diffusive convection is a limiting factor. In a 2021 study, the ice giant's interior conditions were mimicked by compressing water containing minerals like olivine and ferropericlase, thus showing that large amounts of magnesium could be dissolved in the liquid interiors of Uranus and Neptune. If Uranus has more of this magnesium than Neptune, it could form a thermal insulation layer, thus potentially explaining the planet's low temperature. Although there is no well-defined solid surface within Uranus's interior, the outermost part of Uranus's gaseous envelope that is accessible to remote sensing is called its atmosphere. Remote sensing capability extends down to roughly 300 km below the 1 bar, 100 kPa, level, with a corresponding pressure around 100 bar, 10 MPa, and temperature of 320 K, 47 degrees Celsius, 116 degrees Fahrenheit. The tenuous thermosphere extends over 2 planetary radii from the nominal surface, which is defined to lie at a pressure of 1 bar. The Uranian atmosphere can be divided into 3 layers: the troposphere, between altitudes of 350 kilometers, 186 and 31 miles, and pressures from 100 to 0.1 bar, 10 MPa to 10 kPa, the stratosphere, spanning altitudes between 50 and 4,000 kilometers, 31 and 2,485 miles, and pressures of between 0.1 and 10 bar, 10 kPa to 10 Pa, and the thermosphere extending from 4,000 kilometers to as high as 50,000 kilometers from the surface. There is no mesosphere. The composition of Uranus's atmosphere is different from its bulk, consisting mainly of molecular hydrogen and helium. The helium molar fraction, i.e. the number of helium atoms per molecule of gas, is 0.15 plus or minus 0.03 in the upper troposphere, which corresponds to a mass fraction 0.26 plus or minus 0.05. This value is close to the protosolar helium mass fraction of 0.275 plus or minus 0.01, indicating that helium has not settled in its center as it has in the gas giants. The third most abundant component of Uranus's atmosphere is methane, CH4. Methane has prominent absorption bands in the visible and near-infrared, IR, making Uranus aquamarine or cyan in color. Methane molecules account for 2.3% of the atmosphere by molar fraction below the methane cloud deck at the pressure level of 1.3 bar, 130 kPa. This represents about 20 to 30 times the carbon abundance found in the Sunday. The mixing ratio I is much lower in the upper atmosphere due to its extremely low temperature, which lowers the saturation level and causes excess methane to freeze out. The abundances of less volatile compounds such as ammonia, water, and hydrogen sulfide in the deep atmosphere are poorly known. They are probably also higher than solar values. Along with methane, trace amounts of various hydrocarbons are found in the stratosphere of Uranus, which are thought to be produced from methane by photolysis induced by the solar ultraviolet, UV, radiation. They include ethane, C2H6, acetylene, C2H2, methylacetylene, CH3C2H, and diacetylene, C2H. Spectroscopy has also uncovered traces of water vapor, carbon monoxide, and carbon dioxide in the upper atmosphere, which can only originate from an external source such as infalling dust and comets. The troposphere is the lowest and densest part of the atmosphere and is characterized by a decrease in temperature with altitude. The temperature falls from about 320 K, 47 degrees Celsius, 116 degrees Fahrenheit, at the base of the nominal troposphere at 300 km to 53 K, 220 degrees C, 364 degree F, at 50 kilometers. The temperatures in the coldest upper region of the troposphere, the tropopause, actually vary in the range between 49 and 57 K, 224 and 216 degrees C, 371 and 357 degree F, depending on planetary latitude. The tropopause region is responsible for the vast majority of Uranus's thermal far-infrared emissions, thus determining its effective temperature of 59.1 plus or minus 0.3 K, 214.1 plus or minus 0.3 degrees Celsius, 353.3 plus or minus 0.5 degrees Fahrenheit. The troposphere is thought to have a highly complex cloud structure. Water clouds are hypothesized to lie in the pressure range of 50 to 100 bar, 5 to 10 MPa, ammonium hydrosulfide clouds in the range of 20 to 40 bar, 2 to 4 MPa, ammonia or hydrogen sulfide clouds at between 3 and 10 bar, 0.3 and 1 MPa, and finally directly detected thin methane clouds at 1 to 2 bar, 0.1 to 0.2 MPa. The troposphere is a dynamic part of the atmosphere, exhibiting strong winds, bright clouds, and seasonal changes. The middle layer of the Uranian atmosphere is the stratosphere, where temperature generally increases with altitude from 53 K, 220 degrees C, 364 degree F, in the tropopause to between 800 and 850 K, 527 and 577 degrees Celsius, 980 and 1070 degrees Fahrenheit, at the base of the thermosphere. The heating of the stratosphere is caused by absorption of solar UV and IR radiation by methane and other hydrocarbons, which form in this part of the atmosphere as a result of methane photolysis. Heat is also conducted from the hot thermosphere. The hydrocarbons occupy a relatively narrow layer at altitudes of between 100 and 300 km, corresponding to a pressure range of 1000 to 10 Pa and temperatures of between 75 and 170 K, 198 and 103 degrees C, 325 and 154 degree F. The most abundant hydrocarbons are methane, acetylene, and ethane with mixing ratios of around 10:7 relative to hydrogen. The mixing ratio of carbon monoxide is similar at these altitudes. Heavier hydrocarbons and carbon dioxide have mixing ratios 3 orders of magnitude lower. The abundance ratio of water is around 7 times 10⁹. Ethane and acetylene tend to condense in the colder lower part of the stratosphere and tropopause, below 10 mbar level, forming haze layers, which may be partly responsible for the bland appearance of Uranus. The concentration of hydrocarbons in the Uranian stratosphere above the haze is significantly lower than in the stratospheres of the other giant planets. The outermost layer of the Uranian atmosphere is the thermosphere and corona, which has a uniform temperature around 800 K, 527 degrees Celsius, to 850 K, 577 degrees Celsius. The heat sources necessary to sustain such a high level are not understood, as neither the solar UV nor the auroral activity can provide the necessary energy to maintain these temperatures. The weak cooling efficiency due to the lack of hydrocarbons in the stratosphere above 0.1 mbar pressure levels may contribute too. In addition to molecular hydrogen, the thermosphere corona contains many free hydrogen atoms. Their small mass and high temperatures explain why the corona extends as far as 50,000 kilometers, 31,000 miles, or 2 Uranian radii, from its surface. This extended corona is a unique feature of Uranus. Its effects include a drag on small particles orbiting Uranus, causing a general depletion of dust in the Uranian rings. The Uranian thermosphere, together with the upper part of the stratosphere, corresponds to the ionosphere of Uranus. Observations show that the ionosphere occupies altitudes from 2,000 to 10,000 kilometers, 1,200 to 6,200 miles. The Uranian ionosphere is denser than that of either Saturn or Neptune, which may arise from the low concentration of hydrocarbons in the stratosphere. The ionosphere is mainly sustained by solar UV radiation and its density depends on the solar activity. Auroral activity is insignificant as compared to Jupiter and Saturn. At ultraviolet and visible wavelengths, Uranus's atmosphere is bland in comparison to the other giant planets, even to Neptune, which it otherwise closely resembles. When Voyager 2 flew by Uranus in 1986, it observed a total of 10 cloud features across the entire planet. One proposed explanation for this dearth of features is that Uranus's internal heat is markedly lower than that of the other giant planets. As stated previously, Uranus is the coldest planet in the solar system. In 1986, Voyager 2 found that the visible southern hemisphere of Uranus can be subdivided into 2 regions, a bright polar cap and dark equatorial bands. Their boundary is located at about 45 degrees of latitude. A narrow band straddling the latitudinal range from 45 to 50 degrees is the brightest large feature on its visible surface. It is called a southern collar. The cap and collar are thought to be a dense region of methane clouds located within the pressure range of 1.3 to 2 bar, see above. Besides the large-scale banded structure, Voyager 2 observed 10 small bright clouds, most lying several degrees to the north from the collar. In all other respects, Uranus looked like a dynamically dead planet in 1986. Voyager 2 arrived during the height of Uranus's southern summer and could not observe the northern hemisphere. At the beginning of the 21st century, when the northern polar region came into view, the Hubble Space Telescope, HST, and Keck telescope initially observed neither a collar nor a polar cap in the northern hemisphere. So Uranus appeared to be asymmetric, bright near the South Pole and uniformly dark in the region north of the southern collar. In 2007, when Uranus passed its equinox, the southern collar almost disappeared, and a faint northern collar emerged near 45 degrees of latitude. In 2023, a team employing the Very Large Array observed a dark color at 80 degrees latitude, and a bright spot at the North Pole, indicating the presence of a polar vortex. In the 1990s, the number of the observed bright cloud features grew considerably, partly because new high-resolution imaging techniques became available. Most were found in the northern hemisphere as it started to become visible. An early explanation that bright clouds are easier to identify in its dark part, whereas in the southern hemisphere the bright color masks them, was shown to be incorrect. Nevertheless, there are differences between the clouds of each hemisphere. The northern clouds are smaller, sharper, and brighter. They appear to lie at a higher altitude. The lifetime of clouds spans several orders of magnitude. Some small clouds live for hours. At least one southern cloud may have persisted since the Voyager 2 flyby. Recent observation also discovered that cloud features on Uranus have a lot in common with those on Neptune. For example, the dark spots common on Neptune had never been observed on Uranus before 2006, when the first such feature dubbed Uranus dark spot was imaged. The speculation is that Uranus is becoming more Neptune-like during its E. Uranus is the seventh planet from the Sun and is a gaseous cyan ice giant. Most of the planet is made of water, ammonia, and methane in a supercritical phase of matter, which in astronomy is called ice or volatiles. The planet's atmosphere has a complex layered cloud structure and has the lowest minimum temperature of 49 K, 224 degrees C, 371 degree F, out of all solar system's planets. It has a marked axial tilt of 97.8 degrees with a retrograde rotation rate of 17 hours. This means that in an 84 Earth years orbital period around the Sun, its poles get around 42 years of continuous sunlight, followed by 42 years of continuous darkness. Uranus has the third largest diameter and fourth largest mass among the solar system's planets. Based on current models, inside its volatile mantle layer is a rocky core, and surrounding it is a thick hydrogen and helium atmosphere. Trace amounts of hydrocarbons, thought to be produced via hydrolysis, and carbon monoxide along with carbon dioxide, thought to have been originated from comets, have been detected in the upper atmosphere. There are many unexplained climate phenomena in Uranus's atmosphere, such as its peak wind speed of 900 km per hour, 560 miles per hour, variations in its polar cap and its erratic cloud formation. The planet also has very low internal heat compared to other giant planets, which is still unexplained. Like the other giant planets, Uranus has a ring system, orbiting natural satellites and a magnetosphere. Its ring system is extremely dark, with only about 2% of the incoming light reflected, and contains the known 13 inner moons. Further out are the larger 5 major moons of the planet, Miranda, Ariel, Umbriel, Titania, and Oberon, and orbiting at much greater distance from Uranus are the known 9 irregular moons. The planet's magnetosphere is highly asymmetric and has many charged particles, which may cause the darkening of its rings and moons. Uranus is visible to the naked eye, but it is very dim and was not classified as a planet until 1781, when it was first observed by William Herschel. About 7 decades after its discovery, consensus was reached that the planet be named from the Greek god Uranus, Ouranos, one of the Greek primordial deities.